Hi friends, everything that you see around you is called matter. Matter is made up of tiny particles. Do you know how tiny these particles are? For example, how many sugar particles are present in a single grain of sugar? The answer is coming up in this video. We'll explore the characteristics of particles of matter by doing some exciting experiments so that you can get a visual feel of it. For these experiments, I'm going to be using some simple everyday things so you can try them yourself. I'm sure by the end of the video, the concepts are going to be super clear to you and you'll find it easy to remember. And then we'll finish off with our top 3 test-oriented questions on this topic. There were 2 competing theories regarding matter. One said that matter is continuous, and the other says matter is made up of tiny particles. Now, which one do you think is correct? Science is all about validating theories with experiments. So let's go to our experiment table and check which theory is right. Here we have some sugar and a glass of water. Can you see these sugar grains? Now when I dissolve it in water, where does all the sugar disappear? Why is the sugar not visible anymore? And if I taste this water, it tastes sweet. So there's definitely sugar in there. The reason is the water broke up the sugar into tiny particles. So tiny that it's not visible to us. So which theory do you think is correct? That's right. Matter is made up of tiny particles. In this video, we are going to be discussing these 4 characteristics of particles of matter, which are particles of matter are very small. They have spaces between them. They are continuously moving and they attract each other. We are going to understand each characteristic with the help of experiments. Let's look at the first characteristic. Particles of matter are very small. Let's try an experiment to prove this. For that, I'm going to take a very small quantity of potassium permanganate crystals and we are going to dissolve it in 100 ml of water here. Can you see that deep purple color? Now if we can show that a very small quantity of potassium permanganate can also color a large volume of water, then that means that these crystals must be containing millions and millions of particles that get spread on dissolving and color the water. So the particles of potassium permanganate must be very small. But the trick we are going to do is, rather than dissolve a small quantity of potassium permanganate in a large volume of water, we are going to make use of the purple water here. So we are going to take a small quantity of this purple water and dilute it with more water. And then again take a small quantity of that and further dilute it with more water. It's the same effect as adding a small quantity of this in a large volume of water. Let me show you how. First, I have taken 1/10 of this purple potassium permanganate solution in the small beaker here. So 1/10 of 100 ml is, as you can see, 10 ml. Now I am going to pour this solution into the empty glass here. And then we are going to dilute it with 90 ml of water so that the total solution becomes 100 ml. So can you see the light purple color now? Now let's take 1/10 of this new solution and again dilute it with water to make the total volume 100 ml. Again we have taken 10 ml of this light purple solution and we are going to dilute it with water again. So the total volume of the new solution is 100 ml. And can you see the pink color of the solution? And again we are going to repeat the dilution process with this new solution. So even in this last glass, can you see that that light pink color is still visible here? So this process of taking a small part of the colored solution and repeatedly diluting it makes the color go from dark to light. With the help of this experiment, we've shown that if you take the same small quantity of potassium permanganate and put it in a large volume of water, you're going to end up with a light pink color like this last glass here. So what's our conclusion? These tiny crystals of potassium permanganate must be containing millions and millions of potassium permanganate particles, which on dissolving in water, they can spread through the large volume of water and give it a light pink color like this. So the particles of matter must be very, very small. Similarly, a sugar grain is made up of a large number of tiny sugar particles or sugar molecules. Remember, I asked in the beginning of the video, do you know how many sugar molecules are present in 1 grain of sugar? So 1 grain of sugar like the one I have on my finger here. So what's your guess here? Is it 1,000 sugar molecules? Or maybe 1,000,000, 1,000,000,000, 1,000,000,000,000? Or is it a quintillion? That's right. The correct answer is a quintillion. That's 1 and 18 zeros. To help you visualize how much is that, I want you to pause the video here and go and get 1 grain of sugar from your kitchen. So are you ready with your sugar grain? Now look at this sugar grain and say this sentence. There are more sugar molecules present in this single grain of sugar than the number of sugar grains produced per year in the entire world. Unbelievable, isn't it? But it's true. So if you take each sugar molecule in this sugar grain and convert it to a sugar grain, you'll have more than the entire world's sugar. And there, I just ate a quintillion number of sugar molecules right now. Let's place the first characteristic, particles of matter are very, very small, on our concept board. Now let's take a look at the second characteristic. Particles of matter have spaces between them. I'm going to immerse this spoon into this glass of water, and you carefully observe what happens to the level of water. As you can see, the water level rises a bit. The rise in water level is going to be much more clear if you use a larger object. Now I'm going to put the sugar grains in water, and you carefully observe what happens to the level of water. We are going to dissolve this sugar in water. Once we stop stirring, as you can see, there is no rise in the level of water. Why is it so? It's because these sugar grains break up into tiny sugar particles when they are dissolved in water. And these tiny sugar particles go and occupy the spaces between the water molecules. That's why the level of water does not show a rise. So this experiment proves that particles of matter have spaces between them. Now let's visualize this scenario. So imagine we zoom into this glass of water a million times. So how is it going to look? It'll probably look something like this. These white balls here represent the water molecules. And when we put the sugar grains into water, each and every sugar grain is going to look like this gigantic ball compared to these tiny water molecules. So let me put this sugar grain into water. Watch carefully, because this huge sugar grain is going to soon break up into tiny sugar particles, represented by these tiny red balls. As you can see, these tiny sugar particles go and occupy the space between the water molecules. Let's spin the second characteristic. Particles of matter have spaces between them on our concept board. Now let's move on to the third characteristic. Particles of matter are continuously moving. This means that the particles are in continuous motion and on their own. So you don't need to set them in motion. Let's take a look at a couple of experiments for this. I'm going to light the incense stick here. Can you see the smoke spreading on its own? There's no fan or wind in the room. Very soon, the smell will spread across the whole room. This is because the particles are moving on their own. Let me show you another experiment for this. I'm going to drop some potassium permanganate crystals into water, and this time I'm not going to stir it, but I'm going to let it dissolve on its own. Can you see the purple color spreading on its own? So both these experiments prove that particles of matter are continuously moving. Once again, we can visualize the dissolving of potassium permanganate in water by using our bowl of water molecules here. So when we drop the potassium permanganate crystals into water, they break up into tiny particles like this. And since the particles are constantly moving, they spread across the entire liquid. In both these experiments, you can see that particles of different types are getting mixed up. Here it is the smoke particles and the air particles. And in this case, it's the potassium permanganate particles and the water particles. Now, what is the process of mixing up of particles of different types known as? That's right, it's called diffusion. Now, what type of energy do these moving particles possess? That's right, it's kinetic energy. Let's put the third characteristic, particles of matter are continuously moving, on our concept board. Now let's take a look at the fourth and last characteristic. Particles of matter attract each other. A simple proof is, can I break this metal spoon? Definitely not. Or can I break this table? Ow, looks like my hand is broken. So the particles of matter are attracting each other very strongly, and that's why we can't break these. But there are some other examples where the force of attraction is weak, like in this piece of chalk. For example, I can easily break this chalk, or I can cut through the water in this bowl, or I can easily cut through the air. So in these cases, the force of attraction between the particles is much weaker compared to the metal spoon and the table. So these examples show that the strength of the force of attraction is different in different substances. Let's place the fourth characteristic, particles of matter attract each other, on our concept board. Now that we are done with the four characteristics of particles of matter, are you ready for the top 3 questions on this topic coming up for you right now? Friends, go ahead and give these questions a try. And do post your answers and doubts in the comments below. I make a commitment to reply to your doubts as soon as possible. I'll disappear so you can pause the video here and try solving these questions. Isn't it amazing that this massive universe is made up of tiny particles? As we saw in this video, even a single sugar grain is made up of a quintillion number of sugar molecules. That's more than the number of sugar grains in the entire world. And if you enjoyed watching this video, be sure to hit the like button and the subscribe button for my channel. You can also follow my Facebook page. Thanks for watching. Hi friends, do you know what I just did? I just took in the three states of matter: solid, liquid, and air, a gas. So are you ready to explore the three states of matter with me? And then we'll finish off with our top 3 questions on this topic. I'm sure you're familiar with the 3 states of matter: solid, liquid, and gas. When we look at something, our brain automatically knows, is it a solid, liquid, or a gas? In this video, we are going to compare these 3 states of matter in a more scientific way. So we'll compare them based on these 4 properties: shape and volume, compressibility, rigid or fluid, and do they fill their container completely. After that, we'll take a deeper look into solids, liquids and gases and compare them at a particle level. Let's start with solids. Do solids have a fixed shape? Yes. As you can see here, they have a fixed shape. This is a cuboid, this is a cube, this is a sphere, and my watch has an irregular shape. So for solids, the shape does not change. Now, do solids have a fixed volume? Again, the answer is yes, because the space that the solids occupy does not change. The volume is fixed, and we can calculate that volume. For example, the volume of a cuboid is length into breadth into height. The volume of a cube is a cube. The volume of a sphere is 4 by 3 pi r cube. Now, how do you calculate the volume of my watch, which has an irregular shape? That's right, by Archimedes' liquid displacement technique. If I dip this watch in water, then the volume of the watch is the volume of the water it displaces. I actually have a video on Archimedes' liquid displacement technique, so do check it out. Now let me pull out my watch before it stops working. Let's look at the compressibility of solids. Usually solids are difficult to compress. For example, I can't compress the things on the table here. So if I try to take this cube and I try to press it, I can't compress this cube here. There are some exceptions, like a sponge. We'll talk about that towards the end of the video. Are solids rigid or fluid? That's right, the correct answer is rigid, because they have a fixed shape. Fluids are things that can flow. Now, do solids fill their container completely? For example, if I try to put this ball in this container here, does it fill the container completely? The answer is no. Let's add the properties of solids to our concept board. Now let's take a look at liquids. Liquids have a fixed volume but no fixed shape. I'm going to prove these 2 points to you with one single experiment here. For the experiment, I've taken water in this beaker, and as you can see, there's 100 ml of water here. Now I'm going to transfer this water into this container, this one, and this one. And you carefully take a look, what is the change in volume and shape of the liquid. So are you ready? Let's start. Now I'm going to transfer the water from this beaker into this bottle here. And then I'll transfer it to the glass here. Now let's transfer it to the measuring cylinder. So what is the final volume here? As you can see, it's 100 ml, and that's exactly the original volume. So what's the conclusion from our experiment? Liquids have a fixed volume. It was 100 ml all the way through. But they don't have a fixed shape. As you saw in the experiment, the liquid takes the shape of the container it is put in. Let's talk about the compressibility of liquids. If you take a plastic bottle like this containing water, if I try to crush this bottle, it looks like I can compress the water. So are liquids compressible? The answer is no. When I'm crushing it, am I really compressing the water? No, I'm compressing the air inside the bottle. Now if we fill this bottle completely with water, I need to be Superman to be able to crush this bottle. So liquids are almost incompressible, just like solids. Are liquids rigid or fluid? That's right. The correct answer is fluid. The word fluid means it can flow easily. As you can see, water can flow easily. So liquids are fluids. Do liquids fill their container completely? The answer is no. As you can see, in the glass and the bottle, the water only occupies its own volume. The rest of the container is air. So liquids do not fill their container completely. Let's place the properties of liquids on our concept board. Now let's take a look at the third state of matter, gases. Gases have neither a fixed shape nor a fixed volume. Just like liquids, gases take the shape of the container that they are in. One difference is the container needs to be closed. Now liquids have a fixed volume, but gases don't even have a fixed volume. The volume of the gas is the volume of the container. So for example, if I transfer this gas into a larger container, it will fill that container completely. Or if we apply some pressure and try to fit it into a smaller container, then the volume of the gas will be the volume of the smaller container. That brings us to the next point, compressibility. Gases are highly compressible. For example, I can easily squeeze this balloon, or I can easily crush the air in this bottle. Gases are usually stored under high pressure since they are highly compressible. That way we can fit more of the gas in a small container. For example, compressed natural gas is stored in cylinders at a high pressure. Just like liquids, gases are also fluids. They can flow. For example, if I open this bottle, can you see the air flowing out? Of course you can't, because air is colorless. But let's say it was a colored gas, then you would easily see it flowing out of the bottle. In fact, the term fluid is collectively used for liquids and gases. As we discussed before, gases are greedy. They want to fill up the container completely. For example, if this bottle contained a gas and I transferred it to a larger container, then the gas would fill up the larger container completely. Another example is when you open a perfume bottle in a room, the smell spreads to the entire room. So here the room is like a container to the perfume gas. So gases fill their container completely. Now let's pin the properties of gases to our concept board. We have discussed the difference in properties between solids, liquids and gases. But what makes something a solid, a liquid or a gas? For example, if you take water, it can exist in all three forms: ice, water and water vapor. Now it's the same substance, water. So how can it exist as a solid and a liquid and sometimes a gas? To answer this question, we need to zoom into matter and take a closer look. As you may already know, all matter, whether solid, liquid or gas, is made up of tiny, tiny particles. For example, ice, water and water vapor are all made up of the same tiny particles. That is the water molecules. Now let's compare the three states of matter at a particle level based on these 3 points: the distance between the particles, the force of attraction between the particles, and the amount of movement or the kinetic energy of the particles. To get a visual feel of things, I would like you to hold up your hands like this and imagine the tips of your fingers as particles. So are you ready? So this is what a solid would look like. The particles are tightly packed. The distance between the particles is very small. The force of attraction between the particles is very strong. So you have to apply a huge force if you want to change the shape of the solid. Even in a solid, the particles are moving, vibrating about their main positions. But their movement is less. Kinetic energy of the particles is small. Now this is what a liquid would look like. The particles are more loosely packed. The distance between the particles is bigger. The force of attraction between particles is weaker. In a liquid, the particles have more motion as compared to a solid. So the kinetic energy of particles is larger. And now this is a gas. The particles are very loosely packed. The distance between the particles is very large. Force of attraction between particles is very weak. In a gas, the particles are moving a lot. They are going crazy. The kinetic energy of the particles is maximum. Let's add the differences between solids, liquids, and gases based on particles on our concept board. Now that we are done with the 3 states of matter, are you ready for the top 3 questions on this topic coming up for you right now? As we discussed, solids are incompressible. But if you consider a sponge, as you can see, we can easily compress it. So question 1 is, the sponge is a solid. Then why is it compressible? Let me give you a hint. The sponge has holes in it. So what are you really compressing? Now let's look at question 2. I'm going to pour the sugar in this beaker into the glass here. Can you see the sugar flowing like water? And the sugar is taking the shape of the glass. So is sugar a solid or a liquid? The 3 states of matter that we've seen in this video are solid, liquid, and gas. Do you know that there are 2 more states of matter? So question 3 is going to be, what are the other 2 states of matter? Can we make this more interactive than just watching the video? So do post your answers to the questions, or if you have any doubts, in the comments below. And I promise to reply to all your comments promptly. I hope the 3 states of matter are crystal clear to you now. So remember, this is a solid, this is a liquid, and this is a gas. And here's the like button, which I'd like you to hit right now. Also do remember to subscribe to my YouTube channel, and you can follow my Facebook page. Thanks for watching.
Do you know what water, air, and rocks all have in common? They are made of matter. Matter is something that takes up space. Now, you might be wondering why they all look so different if they are made of the same thing. But the truth is that everything around you is made of matter, just in different shapes and forms. Matter is made of tiny particles called atoms. Matter can be grouped into three main states: solid, liquid, or gas. To figure out which state of matter something is in, we need to examine its properties. A property is the way that something is that we can measure. The physical properties we will look at to determine state of matter are shape, mass, and volume. Mass is the amount of matter in an object. Volume is how much space that matter takes up. Solids are easy to recognize. Rocks, apples, pencils, and plants are all examples of solid objects. A solid object has a definite shape that doesn't change when you move it or put it in a container. They also have a consistent mass and volume. This is because the atoms in a solid object are packed closely together, so they do not move around. A solid will change shape only if forced, for instance, if it is broken or smashed. If you look around, you can find many examples of solid objects. Liquid is the next state of matter. Liquids have a definite volume and mass, but they do not have a definite shape. The atoms in liquid are still close together, but unlike the atoms in a solid, they can move around. This allows the matter in a liquid to flow. Because liquids don't have their own shape, they take their shape from their containers. The same amount of liquid may look very different in a glass and spilled on the floor. You can find examples of liquids around you too. Water, milk, and juice are just some of the liquids you might find. The third state of matter is gas. Gases have a definite mass, but they do not have a definite shape or volume. Like liquids, gases take the shape of their containers. Unlike liquids, gases will spread out to completely fill the container they are in. If a gas is not in a container, it will keep spreading out indefinitely. This is because the atoms in a gas are farther apart than atoms in a solid or a liquid, and so they can move freely. The air you breathe is an example of a gas. You might have noticed that you can't really see air. Often, gases are invisible, but they are still there. There are many different types of gases in the Earth's atmosphere, like oxygen, nitrogen, carbon dioxide, helium, and water vapor. Sometimes matter can change from one state to another. Water is a very good example of this. When water is frozen into ice, it is a solid. When it melts back into water, it is a liquid. When water evaporates into water vapor, it becomes a gas. Matter in all its states is everywhere. See if you can find solids, liquids, and gases around you.
States of matter. Matter. Matter is anything that has mass and occupies space. States of matter. Matter exists in three states. 1. Solid state. 2. Liquid state. 3. Gaseous state. Solid state. 1. They have definite shape and definite volume. 2. Ordered arrangement of particles. Distances between the particles are very small and fixed. Intermolecular forces are high. Vibrational motion only. 3. They have high density. 4. Particles are nearly incompressible. 5. They are not fluids. Diffuse very slowly, only through solids. Liquid state. 1. They have no definite shape, that is, assume the shape of the container. Have definite volume. 2. Disordered clusters of particles. Quite close to each other. Random motion. Considerable intermolecular attraction. 3. They have intermediate density. 4. They are slightly compressible. 5. They are fluids diffused through other liquids. Gaseous state. 1. Gaseous have no definite shape and no definite volume. 2. They are extremely disordered particles. Much empty space. Particles have random motion. Intermolecular attraction is very small. 3. They have low viscosity and density. 4. They have high compressibility. 5. They are fluids diffuse rapidly. Important points about gases. 1. Number of gaseous elements are 11. Hydrogen H2, helium He, neon Ne, argon Ar, krypton Kr, xenon Xe, radon Rn, nitrogen N2, oxygen O2, fluorine F2, chlorine Cl2. 2. Most reactive gaseous element is fluorine. 3. Lightest gaseous non-metal is hydrogen. 4. Heaviest gaseous non-metal is radon. 5. Noble gases have lowest electron affinity. 6. Highest ionization potential in noble gas helium. 7. Most abundant inert gas in Sun's atmosphere is helium. Eight. Most abundant inert gas in atmosphere is argon. 9. Most abundant element in Earth crust is oxygen.
Today we'll be learning about changes in the states of matter. Now you know there are 3 states of matter. There are solids, there are liquids, and there are gases. And you probably know that when a solid like ice turns into a liquid, we say that it's melting. And if a liquid like water turns back into a solid, we can say that it's freezing. But it turns out they're names for all of the other types of changes that can exist as well. If a liquid turns into a gas, like when you boil a pot of water, we say that the liquid is evaporating. This is an example of evaporation. There are also times when a gas will turn back into a liquid. If you've ever had a bottle of cold water, you see these little droplets of water form on the outside. This is happening because water vapor, or gas in the air, is turning back into a liquid because of the cold water inside of the bottle. We call this process when a gas turns back into a liquid condensation. There's one more example too. Believe it or not, but a solid can turn directly into a gas without ever having to be a liquid. This happens with dry ice, which is solid carbon dioxide. If you drop it in some water just to start the reaction, you can see that the carbon dioxide ice is turning directly into a gas. It's never becoming a liquid. Those solid chunks are switching directly into a gas. Now this process where a solid goes straight to a gas is called sublimation. Let's practice some of these together. If you ever wake up on a cold morning, you sometimes see that there's liquid water on the grass. This water comes from water gas or vapor in the air that's turning back into liquid water. What is it called when a gas turns back into a liquid? Well, we can see that that is called condensation. Here's another example. If you pour water on a dark surface on a hot day, you can watch it seem to disappear really quickly. That's because the liquid water is turning into water gas or vapor and vanishing into the air. What is it called when a liquid turns into a gas? Well, you can see that we call that evaporation. Finally, here's one more. When you have a cube of dry ice, solid carbon dioxide, it turns straight from a solid into a gas. What is it called when a solid turns into a gas? Well, when a solid turns directly into a gas, it's called sublimation. Now it's time for you to practice on your own. On cold days, you sometimes see droplets of water form on your window. What is happening to cause that? Well, that's happening because water vapor or water gas in the air is turning back into a liquid on your window. That is an example of condensation. Now here's another. When you boil a pot of water, say to make tea, you can see all of this gas coming out of the kettle. What is this an example of? Well, in this example, liquid water is turning into water gas or water vapor as you boil it. This is an example of evaporation. So from today, remember, evaporation is when liquids turn into gases. Condensation is when gases turn into liquids. And sublimation is when solids turn directly into gases.
States of matter. In this video you are going to learn what the three states of matter are, some examples of each state of matter, the characteristic properties of the three states of matter. The three states of matter are solid, liquid, and gas. Let us look at solids. An example of a solid is your computer. The properties of solids depend on how the particles in solids are packed. In a solid, the particles are closely packed in fixed positions and cannot move anywhere. So, solids are rigid, cannot be squashed or compressed, have a fixed shape and a fixed volume. They cannot flow. Now let us look at liquids. An example of a liquid is water. Just as with solids, the properties of liquids depend on how the particles in liquids are packed. In a liquid, the particles are again closely packed, but not as closely packed as in solids. So this means the particles in liquids can move around each other. So, liquids are not rigid, but because their particles are closely packed as in solids, they cannot be squashed or compressed. They do not have a fixed shape, but they do have a fixed volume. Beware with that one, as many students think because liquids do not have a fixed shape, they do not have a fixed volume either. But they are wrong. If someone orders a pint of beer, they cannot make it 2 pints by pouring it into different containers. As you know, liquids can flow. Finally, let us look at gases. An example of a gas is helium. This is the gas in party balloons because it is less dense than air and unreactive. Again, as with solids and liquids, the properties of gases depend on how the particles in gases are packed. Unlike solids and liquids, the particles in gases are not closely packed, they are far apart. As a result, gases are not rigid and can be squashed or compressed. They do not have a fixed shape nor fixed volume. They fill the whole space they are in.
There are 4 states of matter in the universe: plasma, gas, liquid, and solid. But matter on Earth exists mostly in 3 distinct phases: gas, liquid, and solid. A phase is a distinctive form of a substance, and matter can change among the phases. It may take extreme temperature, pressure, or energy, but all matter can be changed. There are 6 distinct changes of phase which happens to different substances at different temperatures. The 6 changes are: freezing, the substance changes from a liquid to a solid. Melting, the substance changes back from the solid to the liquid. Condensation, the substance changes from a gas to a liquid. Vaporization, the substance changes from a liquid to a gas. Sublimation, the substance changes directly from a solid to a gas without going through the liquid phase. Deposition, the substance changes directly from a gas to a solid without going through the liquid phase. I'm sure you know what most of these phases look like. Freezing is when liquid water freezes into ice cubes. Melting is when those ice cubes melt. Condensation is when dew forms on grass in the morning. Vaporization is when water boils and turns into steam. Deposition is one you may not know, but this happens when water vapor goes directly to freezing, like when there is frost on a cold winter morning. An example of sublimation happens when dry ice turns directly into gas. Gas can also change into a plasma. In order to do this, you have to add an enormous amount of energy to the gas in order to free up the electrons from the atoms. Let's take a look at phase change as it pertains to water. This will apply to all substances, but we are all most familiar with water. Phase change is often shown in a diagram like this one. When a substance is in a solid state, it can absorb a lot of energy in the form of heat until it hits its melting point. Think about snow outside. Once snow hits the ground, it stays there, whether it is negative 50 degrees Fahrenheit outside or all the way up to 32 degrees Fahrenheit. The snow can absorb energy all the way up until it hits its melting point of 32 degrees Fahrenheit. This is the diagonal line at stage 1 on the graph. Once a substance hits its melting point, it is a combination of a solid and liquid for a while, as you can see by the flat line on the graph at stage 2. At a certain point, all of the solid has turned into liquid. Now the liquid can absorb energy in the form of heat for quite a while until it gets to its boiling point. Think about putting a pot of water on the stove and waiting for it to boil. You start with the water at whatever temperature it came out of your tap. Then you add heat for quite a while. The water gets hotter and hotter, absorbing more and more heat, but it is still all in the liquid stage. This is stage 3 on the graph. Eventually, after what seems like forever if you're hungry, the water gets to its boiling point. At this point, the water starts to boil and turn into steam, or water vapor. For a long time, the water is in both liquid and vapor stage, stage 4 on the graph. If you wait long enough, all the water will eventually turn into steam, and all of the liquid will be in a gaseous state, stage 5 on the graph. Now here's the weird thing about this diagram. Notice that at phase 2 and 4, when a substance hits its melting point and boiling point, no change in temperature happens. Energy is still being added to the substance, but the temperature doesn't increase. This is because at those points in the process, all the extra energy is being put into breaking the bonds between the molecules of the substance. This is also true of the other 4 changes of phase: freezing, evaporation, condensation, and sublimation. Energy is either being used to break or form bonds, and that is why the graph is flat at that point. Although we have talked mainly about water in this video, all substances have specific phase change temperatures. Also, freezing, melting, and condensation points can change for different substances depending on the pressure they are under. If you try to boil water at a high altitude, you know that water boils at a lower temperature due to the lower pressure at that altitude. Substances on Earth can exist in one of 4 phases, but mostly they exist in one of 3: solid, liquid, or gas. There are 6 changes of state that substances go through: freezing, liquid to solid; melting, solid to liquid; condensation, gas to liquid; vaporization, liquid to gas; sublimation, solid to gas; deposition, gas to solid.
Matter. Since early times, human beings have been trying to understand their surroundings. As we look at our surroundings, we see a large variety of things with different shapes, sizes, and textures. Everything in this universe that we see is made up of material, which is called matter. Matter occupies space and has mass. All matter is made up of tiny particles. If we were to observe sunlight falling through a window, we would be able to see tiny particles floating in the air. These particles have spaces between them. Let's demonstrate that using the example of salt dissolved in water. When we dissolve salt in water, the particles of salt get into the space between the particles of water. Also, you will observe that there is no change in the water level. Thus, we have found that particles have space between them. You will also see that the particles continuously move. A drop of ink slowly spreads in water. Matter around us exists in three states: solid, liquid, and gaseous. Matter in the solid state has definite shape and volume. This is because the particles in solid are tightly packed, fit together in a regular way, and there is no big space between the particles. Therefore, the force of attraction between the particles is very strong, and the only movement they make are tiny vibrations to and fro. That is why solids are rigid and retain their shape. If we take a stone and put it in a box, the pebble retains its shape. Matter in liquid state has no fixed shape but has a fixed volume. In liquids, the particles are most closely held together but are not in a fixed pattern. Particles move freely and have greater space between each other. Because of the greater space between the particles, the force of attraction between the particles is weaker than in the solid. Matter in gaseous state has no definite shape and no definite volume. In the gaseous state, the particles are far apart. There is a lot of space between the particles and they move about randomly at high speeds. Due to the huge space between the particles, there is no force of attraction. When a stone is dropped into a beaker with water, why does the stone sink into the water? Let us explore. Generally, the density of solid is high compared to liquid and gas because there are not big spaces between the particles. Gases have much lower densities than either liquids or solids. Let us examine compressibility, another attribute of matter. These are empty syringes. Close the nozzles of the syringes with rubber corks. Fill one syringe with chalk pieces, fill another with water, and leave one syringe empty. Insert the piston and try to compress the material in the syringe. You will see that the syringe with the solids is not compressible because the solids are rigid. The syringe with water is compressible because there is greater space between particles compared to solids. The syringe which is empty is easily compressible because the particles in a gas, in this case the air in the syringe, have more space than solids and liquids. This experiment shows that gas is highly compressible compared to solids and liquids. Yet another attribute which differentiates solids, liquids and gases is diffusion. When perfume is released into the air, the fragrance spreads very fast. This is due to the movement at high speed of particles and the large space between them, thereby gases show the property of very fast diffusion. Liquids have less diffusion when compared to gas. In solids, diffusion is negligible. Things to remember. Matter exists in three states: solid, liquid and gaseous. Solids have definite shape and volume. Liquids have no fixed shape but have a fixed volume. Gases have no definite shape and volume. The spaces in between the constituent particles are minimum in the case of solids, intermediate in liquids and maximum in gases. The forces of attraction between the particles are maximum in solids, intermediate in liquids and minimum in gases. Generally, density is very high for solids, moderate for liquids and much lower for gases. Generally, compressibility and diffusion are negligible in solids, moderate in liquids and very high in gases.
When a solid gets warm enough, it melts. To explain what's happening, imagine you can see how the particles in a solid are arranged. They're in a fixed framework, vibrating but not straying far from their main position. When energy is supplied, the particles vibrate more violently and become free to move. The solid changes into a liquid. Melting involves a transfer of energy. This can be illustrated by putting an ice cube in a sealed container, leaving another one empty. The air on the left is at 25.5 degrees Celsius. As the ice melts, it takes energy from the surroundings. The temperature of the air in the right-hand container has fallen by about 3 degrees. Energy is also needed to change a liquid to a gas. So, what's happening to the particles this time? In a liquid, the particles are free to move around. Heating causes them to move around more quickly. Those which have enough energy escape from the liquid, forming a gas. This is evaporation. Ether evaporates at room temperature. It's taking energy from the surroundings and disappears in less than 5 minutes. It's possible to see how different liquids take heat from their surroundings using thermometers wrapped in string. They all start off at room temperature. The string absorbs the liquids. Number 1 on the left is a control. Number 2 is dipped into water, 3 into ethanol and 4 into ether. As soon as the string leaves the liquid, evaporation gets underway. The temperature of thermometers 3 and 4 quickly begins to drop. As the liquids evaporate, they're taking energy from the string, the air, and even the bulb of the thermometer. So, which has taken most energy from its surroundings? Liquid 2, 3, or 4? Gases can also be changed into liquids. For this to happen, they need to be cooled. Liquid nitrogen is extremely cold. Immerse a balloon full of air in it and see what happens. The balloon shrinks and becomes brittle. Inside, you can see a liquid. It's liquid air. This time, the balloon is filled with carbon dioxide gas. Immerse it in liquid nitrogen and it cools rapidly. What's inside the balloon this time? If a gas gets cold enough, it changes into a solid. This is solid carbon dioxide. See how it changes back to a gas at room temperature.
You may have learned about the 3 states of matter, solid, liquid, and a gas in a previous lesson. Did you know that there is a 4th state of matter, plasma? In this lesson, we will learn about plasma. Let's start by thinking about ice. When ice is sufficiently heated, it melts to form water. It has therefore undergone a change of state, from a solid to a liquid. Recall that in a solid, all of the particles are closely packed in a fixed position, and therefore has a fixed shape and volume. The particles in a liquid are still touching one another and are able to move around each other. Therefore, a liquid still has a fixed volume, but it takes the shape of their container. What is the change of state that occurs
when water is heated to 100 degrees Celsius? Pause, think, and continue when ready. The answer is water evaporates from a liquid to a gas, in our case, water vapor. The particles in a gas are further away from one another and take the shape and volume of their container. For certain substances, if we continue to apply heat to their gaseous form, another change of state could occur. These substances can go from a gas to a state of matter called plasma. For this change of state to occur, very strong heat must be applied. When heat is sufficiently strong, the electrons are stripped from their respective atoms, creating free electrons and positive ions. Although there are both negative and positive particles, plasma is neutral overall, as there are equal amounts of oppositely charged particles. Since free electrons are present, substances in plasma form can conduct electricity. This is what separates a gas from plasma. All gases cannot conduct electricity, but plasma can. Naturally occurring plasma include lightning and the northern lights. If we were to go far beyond planet Earth, stars also exist in plasma form. In fact, stars are really just hot balls of plasma. Plasma can be found in fluorescent light bulbs and neon signs. When an electrical current is passed through the mercury vapor in fluorescent light bulbs, it heats up the gases sufficiently to strip the electrons and to create plasma. Plasma screen TVs are made possible due to this state of matter. A plasma screen is made of many thousands of tiny dots called pixels, which are made of 3 fluorescent light electrodes emitting the colors red, green, and blue. The combination of these colors can give any possible color, which is why we can see all colors on these screens. The higher the number of pixels, the higher the definition, and the images will appear sharper and more detailed.